Hi, so I'm Jackson Van Dyke. I want to start by thanking the organizers for the opportunity to speak here. I was here last week too. It was a really stimulating school, and I looked up to a lot of the speakers this week, and I'm really excited to hear what they have to say because the abstracts look great and they're all great speakers. Okay, so I want to talk about projective 3D TQFTs. I think in a lot of ways, what I'll say is probably a specialization of things that we'll hear later in the week. So I'm excited to hear those talks, as I'm sure everyone else is. And so I want to sort of give something that will definitely start very comfortable introductions to these kind of 3D TQFTs. And so the first part really I just wanted to sort of crash course in 3D TQFTs, sort of either very finite things, so we'll know value huge, and I'll say in detail what everything is in the first part. And then I'm going to make it really clear by the word projective in this context. I think that word gets used in different ways in this context, and so I'll be precise about what I mean. And really what that means is I'll write down what I mean by projective target categories. So these theories are all functorial, and so I need to tell you what I mean by projective theory by telling you what the projective target is. And now, the third part, I want to attempt to make some connection with. So if you're not the sort of person who sort of thinks primarily about these very finite objects, I want to make an attempt to explain how some version of the story that I tell in the first two parts may also hold in a more enriched setting. And so maybe the third part, I'll call this condensed targets. And you'll see what I mean by that. You got it. So someone can tell me if my boards just get beyond where C. Okay.
This you can see on the camera.
Okay, super.
Yeah.
Okay, thank you.
Just above.
Oh, I can see here actually.
A little to the shadow above the lower.
Yeah.
Thank you. Okay, so I just want to say what I mean by 3D TQFT in the first part. And so before I say anything super technical, I just want to get sort of everyone on the same page about what I mean by this. And so for me, the starting point, and this isn't the starting point for everyone, and so that's why I'm going to sort of explain a dictionary between my starting point and yours. So the starting point is some and maybe for various purposes manually written category. And throughout I'll write strict A for this object. And this is sort of the thing that encodes what we start with. And so you can think, depending on what kind of person you are, you can think that this is a category of anions or superselection sectors. So we learned how these sort of assemble into this kind of structure from Peter last week. And then maybe, so this is sort of the same thing, but maybe the category of line operators and the figure that you start with, and maybe this is quantum. So quantum, sometimes quantum group representations, if you want it to be some maybe small, say quantum group, or maybe even more mathematically concrete, you might just think that it's a category of space is created by groups. And so these various things will come in a more detailed way back later in the talk, but I just wanted to give some thing for people to grab onto if you like some of these objects better than others. And I'll say things that are much more concrete, but just to get everyone on the same page. Okay, and so I should say once and for all that for me, a TQFT is a representation of the order of the category of some kind. I think with some target, and so just it's just problem is really working. I'll in this sort of a TFC goal formulas, and I'll make use of the cobordism hypothesis. Sort of work with the notions that are variance subject.
That's going to be hard to read.
Oh, sorry. Okay. So I said that I'm going to do 3D TQFTs, and those are typically valued in 3 categories. Now I want to take the perspective that before I talk about the 3D theory, it might sort of come to me as an anomalous theory or something, and I'll say what I mean precisely by that. But in terms of the setup, what this means is that before I specify the 3 category, I'm going to specify the 4 category, and I'll make this very concrete. So if you don't like higher categories, this should be still something you can grab onto. Okay, and so I want to sort of take advantage of formalism that's in those in 3 power. The even higher rated category, and also Claudia's work on that. The normal higher rated category, not even higher, and then sort of in detail for this dimension, I want to use instructions from grocery driven Snyder and grocery driven Saturn. Okay, so in detail, the target that I'll write down is a 4 category called review. The objects, we can think of them explicitly as being given by, so finite, semi-simple, rigid, equation like that. And I told you that it was a 4 category, so I need to tell you a lot more information than just this. So the one-morphisms, these are bimodular categories, but they come with a compatible monoidal structure. And so the idea is that when I'm grading, it's really sort of 2 monoidal structures. And when I say modules or bimodules, I'm only using up one of those, and so there's one left. So these are again bimodule categories. And now the 3 and 4 morphisms are given by functors and natural transfer. And there are finite distributions out of bimodular categories as well that I didn't write, but there. Okay. So now there's a 3 category thing inside of this, which is one way of writing this endomorphism of the identity in this. And this is well-approximated is huge. And so this is the category of just monoidal categories with bimodular categories, functors, and natural transfer.
So is this like the morphism 3 category of something to itself? And if so, what objects?
Sorry, this is my notation for an inverse view of vectors.
Okay.
Thank you. Okay.
Can you say what are the objects of this category?
Yeah, so the objects themselves are categories. They're finite and simply rigid, but those are just semantic tips. The main structure is that they're braided monoidal things. So
is this a monoidal 4 category?
Yeah, this is a, but this is a symmetry.
What's the tensor product?
Sorry?
What's the tensor product?
So the tensor product is an underlying categories, it's like the domain tensor product. And so it's like when you take the tensor product in the Morita category of algebras, it's the tensor product of degrees at the level of taking it on with the like tensor product of the categories. Right, so as suggested by those questions, we're all on the same page that this is going to be a target for TQFT. So let me tell you about the kinds of theories that I'm going to think about. Okay, so the theories I'll think about are invertible ones. And so again, starting with A, that'll be the starting point throughout. We'll find so. All right, the theory is alpha sub A. The four-dimensional TQFT value is target.
Sorry, there's a question in the chat.
Oh, yes.
So in the context of canonical quantum field theory, how is that these 3 and 4 categories emerge?
So one way to think about, so in terms of the 4D TQFT, one way to think about the morphism categories in the target is as giving the higher categories of defects of various codimensions. So one way to think of all the structures that are sort of assembled together in this big 4 categories is encoding some defects in various lower dimensional theories. So that's actually sort of the point of this TQFT. So if you write down a 3D theory with an anomaly, one way that anomaly is often encoded is by a vertical 4D TQFT. So one way to think about this target is the place where you can sort of do various homotopy theoretic calculations that detect an anomaly in your theory. So these 4D theories will send numbers to top dimensional things, and sometimes it can be thought of as detecting whether it be 3D theory on its boundary as an anomaly. So that's one maybe slightly more physical remark I can make about these targets. Okay, so for this, I want to now make a bunch of citations. So this is morally, and so I say morally because there's a slight conjectural component that I wrote that is explained by the Gordon hypothesis. But morally, this is the parameter forming of full invariant theory. And so one sort of sense in which that's only morally true is that what I told you so far in the defined frame TQFT, I didn't tell you that there's some homotopy fixed point structure of SO that's relevant here. And if it was oriented, you could make a comparison. What's the one that just so or like BPSS with this invertibility statement, and then I want to just so there'll be some other, well, say on the next board, I'm going to talk about its relationship with 3D theories, and there are lots of other people that I want to name as being relevant for this story. And I'm going to say as a sort of specific instance of the theories that look like that. So, like I said, most of the so I won't tell you the homotopy fixed point structures of SO. So using the Gordon hypothesis, I won't tell you the oriented theories, but that's really a random structure which I wrote for all the examples we'll consider these categories to have. We'll give you the appropriate oriented structure for this theory, and then what I say will also hold for those oriented theories. So this is really the only thing I want to say about oriented theories is that so there's oh yes.
TQFT, so which category of borders are framed right now?
Yeah, so the way I told you it so far is I defined the Gordon hypothesis, which is just framed, and so now I'll just say so effectively the structure on the product. And in a moment on the next board, I'll write about 3D theories that live on the boundary of this, and so they'll really only see board 3 because they're natural transformations. And so you maybe are only interested in an SO3 fixed point structure. Okay, and so I just want to say something very quickly in this example that there's no, so we're going 4D theories. It's on the 4 manifold to some scalar raised to the ordinary characteristic and another scalar. And so for this 3 says some news written about these invertible theories and also okay, so just to say something very concrete about these 4D theories, that even though there's a lot of this hard categorical stuff that I wrote on this board, that they can be realized in a more concrete way and make contact with things that are maybe more comfortable.
Sorry, one question maybe. Is this your functor? It's what? It's like a graded monoidal functor. It's some higher functor.
Yeah, so this, my functor alpha that I wrote there, it's a symmetrical functor of 4 categories.
Okay.
And so it restricts the disjunct union of 4 and sends that to the symmetric angle product in the target. And so one fact that I didn't write, so I looped it once and I got to fuse. If I loop it again, I get to just the 2 categories with no Marita, or the Marita 1 category of algebras. And then if I loop it again, I get to that. And so I wrote here Green-Yetter, which is really just a sort of non-extended TQFT. And so the claim that is implicit in this conjecture is that in low codimension, this functor agrees. So if I, for example, define that using factorization homology, then in low codimension, it would agree with the functors that you write down just into back. And so you should think that this is sort of a higher generalization of that, but then when I take loops the appropriate number of times, is giving me the structure that disjunct meaning that D-1 Bordisms goes to tensor product.
So do you know which fusion category belong to, like, corresponds to that theory that you wrote down with the like characteristic?
Yeah, so maybe on the record, I won't write the formula down, but in terms of these numbers that you can calculate from the fusion category, so given a specific element, so the width class doesn't quite pin down these scalars, but if you give me an actual graded fusion category presented in some explicit way, you can calculate these scalars, and then that's what the theory spits out. So it's this like P plus over P minus full dimension.
Oh, so it's like every theory had this partition function. So what you said? Oh.
That's right. Yeah, so there are these facts about how sort of there's this Euler part of the theory, and then you can sort of deform away, and then there's the signature part that's maybe more sort of a fundamental Bordism invariant that 4D theory is defined by.
Can I?
Yeah, please.
Are you thinking a particular model for categories?
Yeah, okay, so that's a great question. So something that they also explained a bit in Roche Jordan Snyder and Roche Snyder. So formally what's going on here, as I said, is I'm using this even higher Morita category formalism to form the 4 category. And so this is an infinity 4 category. Later, I'll make explicit constructions of these projected targets, and I'll be using complete and full Siegel spaces. I mean, that's what I use in the proof. What you should imagine to make contact with sort of abelian category theory, things that, you know, that like if you read EGNO and things like this. So the thing to think is that this sits in some, it's the infinity category, Morita category, and that the objects are incompletions of abelian categories. And so you can leverage facts in the world of abelian categories through things in this target, taking advantage of an equivalence between this Rex category and a certain subcategory the higher EV2 category. So yeah, so I kind of wanted to avoid the technical things, but yeah, that's the setup that I'm working in. Yeah, no, next week, but okay. So these theories, the role they play for the rest of the talk is as the anomaly of the 3D theory. And what I really mean by that is that when I consider twisted or relative 3D. And so here I want to mention something. So Heidegger wrote about these things as twisted theories, and Telemann wrote about relative theories. And so the formulas that I'll work in, as I just mentioned, was in the sort of higher categorical world of Johnson through Scheinbauer. And so the sort of upshot of that formalism in this context is that, well, it is a twisted theory. So natural transformation. So really there's a missing adjective, complex or complex, which I'll sort of try not to talk so much explicitly about, but it is important that that's there. And so they're natural transformations from the trivial theory to the theory in question. And so if we're doing 3D theories twisted by invertible 4D theories, then we'd be looking at natural transformations between the trivial functor like this and this non-trivial one, but still invertible. Okay. So if I want to use the coordinating hypothesis for these things, and so the H classified by appropriately dualistical or non-dual, so dual modules, and over A, and so these are really morphisms back to A in group. So these are also many. Okay, so the point is that if I have this functor of 4 categories, it's classified by where it sends the point. And then if I'm looking at maps between those functors of 4 categories, it's classified by the map between the assignments to the point. And that's this guy. And so M is a module category. It's also a module category for A, and it's compatible in the sense that there's a map from A to the principal center. And so there's one sort of canonical example of this breakdown, which is the regular school. And so now there's an idea that's been around for a long time to various people, which is that this classifies something that deserves a name WRT associated to A on the boundary of alpha. And so, of course, names of cycle with representation drives. Although Walker had ideas, this is Reuter. And then so some things where this was sort of also a project of Scheinbauer Telemann takes this perspective and then reason work and puts this sort of into practice.
So what's the subscript of A? Is it AA?
Yeah, sorry. So I'll make that a little neater. So
Thanks.
yeah, that's just the regular module of A. And so I wrote the subscript to remind us that it's sort of living in a different ambient category than A. So okay.
The regular
And so
module
let me explain how this is compatible with what you might know already about refugee contrived theory a little bit. I'll make it compatible with what I know about refugee. Okay. Yeah, so maybe I actually want to make a remark about this, which is So. And this will come up at the end of the talk, maybe more importantly, but just to make a brief remark while we're at this. So even when so this trivializable. So it's sort of very often the case that this theory is trivializable as a frame theory. You know this, depending on how generally you're willing to take it. As an oriented theory, it's less often that it's trivializable. If you introduce extra tangential structure, like a P1 structure or a signature structure, then there are theorems to the effect of it always being trivializable, and same with the frame case. And so you might be sort of saying to yourself, why is he talking so much about this 4D theory when I feel like in practice I can just sort of erase it by doing some tricks, and so that's true. But I want to know even when this is trivializable. So actions of group on A, which happens a lot, I claim, give rise to so actions there. So give actions, let's see on this anomaly theory. And the point is that oftentimes actions of G on A do not give rise to actions of G on projective theory, but only projective. And the fact that it acts coherently on alpha is sort of one way to formally say that mod, it's formally for that mod. So they do this. With the anomaly theories, formally dating those symmetries with new theories that are still invertible, which are related to solve it, they would say, related to invariance and indices. Yeah. So I'm thinking of the sort of thing where you have a, so say something just very briefly now about lattice models, if you just out loud. So there's some belief that if I have a lattice model which is gapped, then there's an equivalence between a TQFT that's supposed to represent that at low energy. And so the idea here is that there are these sort of algebraic descriptions of some homology classes and different objects that appear in the study of symmetries of those things. And then in the context of the lattice model, you can sort of also cook up these invariants and indices of those systems, and one might imagine abilities looking at those instructions. So it's just a remark to say that even when the theory is trivializable, its existence and its symmetries can be interesting.
Sorry, could you perhaps repeat the?
So I'll do a very explicit example next. But before that, I'll stop for questions.
So sorry, could you perhaps repeat
What is
the?
to write to set that this as a
I don't think very.
as the ipsu particle is represented by some I'm not sure whether it's fused some that's a category, but to write is something modular.
Right. So yeah, I didn't say the word modular, but yeah, every example that I'll consider is in fact secretly modular, and so it has a ribbon structure, and it has so it satisfies modularity, and it in particular, so I'll assume non-degeneracy at some point, which ensures that this is an invertible theory, which is one of the things that's ensured by modularity when you really start with an MTC. And so, yeah, thank you for pointing out that, yeah, I really am starting with something that's different than what one usually starts with in that story. But in the examples that I'll consider, that structure is there in the background. Oh, sorry. Yeah, the question was, so usually when you read about Whitmer-Deacon-Triumph theory, the starting point is from a modular tensor category. So something that has a ribbon structure and more than what I wrote in the talk. And so I was just saying that in practice, that is what you have, but for the theorems that I want to discuss, that structure is less important, so I didn't mention it. But thank you for the question.
Just to clarify, so
Yeah.
does it make sense to define, say, WRT invariant of three manifolds using any braided fusion category?
Okay, so I'll say something about that. So what you get from one of these objects, so if I start with the non-degenerate braided fusion category, this won't have the oriented structure, and so this is where this conjecture came in being worked. So the Rubin structure helps you with that, but you do still get convertibility as long as you assume no objects.
Oh, right, you need to. By the way, okay, but if it's not modular, then you still get invariance, just not.
Yeah, so it's a question of
Like
what tangible structure you put up the manifold, basically. They said if you're willing to equip it even with the framing, then everything will be okay. But this is sort of more than you get in practice. But a student theories like that. Okay, so now I'm going to give an explicit example that hopefully makes slightly more contact with so people have seen. So let me take the example where this MVC that I start with is the Greenfeld center, which already means that it will be very easy for E theory. But I'll even assume that it's the Greenfeld center of a very easy category, which is just vector spaces created by some Zalian groups. Finite group with convolution structure. And so this can be given an explicit description. This is vector spaces created by a new finite Zalian group, which is L plus its character dual. And it gets a braided structure from the evaluation formula, which I won't write explicitly. But I want to use this example to point out how this anomaly formalism works. So what I told you is that I'm thinking that these relative theories are really natural transformations from 1 to alpha. And so the claim is that WRT is some natural transformation like this. And now what I claim is that when the categories of this form, I actually have a trivialization, which is an equivalence and vertical natural transformation from alpha to the trivial theory. And that on the point, so this is very low, right? These things go on the point, so I just get that. That. This is A, this is the regular module. And my claim is that the label for this arrow is the bimodule category vector. So vector L has an action of its own center. The centers act on the things they're centers of. And my claim is that that's an invertible Morita map. So this is analogous to how matrix algebras have Morita trivializations given by their defining representation. And then tensoring with the regular module sort of forgets that action. And so what's happening here is I'm composing these. So I'm tensoring them. So I get vector L tensored over A with A, which is. And so in other words, this composed arrow is 3D defining group L, and I didn't write a twist, so there's no twist. Could have put a twist here, and then this wouldn't have such a nice form, but. So this is really sort of the Simpson, there's a motto that if we can try for the Greenfeld center of a fusion category is try to zero for that fusion category. So in the context of what I said so far, that's sort of what that motto is. Okay, so now I want to shift gears a bit and talk about projective TQFTs.
There's another question in the chat. That's a follow-up from the earlier question.
Okay, great.
Still, I don't understand how is that classical quantum field theory give rise to these structures. For example, Gordon fields seems a little artificial to me. The definition and use of this convertibility.
So, yeah, so I think maybe to make contact with more traditional. Yeah, so this is a bit abstract. So in low dimension, which I'll say a little bit about, I think make a little more sense. So in low dimension, you should think that the 3D theory is sending a surface to a Hilbert space. And then I'm saying that this theory, if it's anomalous, that Hilbert space might actually, or rather, let's say the partition function. So I add some string until it gets sent to some number, and if it's anomalous, and that number is really a section of a line or a line bundle, maybe over some space, if it's anomalous as a theory, as a family of theories, and that maybe is making more contact with traditional perspectives. So this is really just trying to do an abstract generalization of this in a fully local setting, so that when I integrate onto a code dimension one thing, I can try to retrieve something that is more typically thought of as quantitative theory. Okay. All right, so now I want to shift gears a bit and just talk about this projectivization construction. So right, so for this, I want to talk about sort of, rather than trying to generalize the story I said so far by hand to a more analytic setting, I want to abstract the structures that we saw and try to just apply them to more analytic targets. That's sort of where I want to go with the rest of the talk. Okay, so let me try to say something very general. So I'm studying anomalous theories in dimension D. So I'll say that these sort of with a target category, and I'll say that it's loops in some D+1 category. And so D+1, so this is a symmetric monoidal D+1 dimension target. And so if you like non-extended theories, you can take that to just be something like algebras that moves down to effect. And if you like extended theories, then this would be something that categorifies the target for oh yeah. So there's the working example that I'll put maybe at the bottom, which is that. So and so this will be the target for the anomalic theory. So in 3D, that will be perfused. And if you like non-extended theories, that's the Murray category. And I'll write that explicitly. But the point is that we start with this higher category. And there's this lower target, which is loops in it. And then there's something that sits in between, which is this projectivization. And so this thing really does depend a bit on T, and that's why I write the notation this way. And I'll say sort of in what ways it does. It's sort of mild and low categorical level. And the main thing to know about this construction is that there are two functors. And that this is in some sense exact, so that there's a trivialization of the composition base. And so just to give you a sense of how that sort of exactly plays out in practice, I want to think that maybe I start with an object of my ordinary target, so the fusion category, for example. And I look at its automorphisms. So I'm going to tell a story about symmetries, and so I'm going to look at automorphisms. And then there's this sort of image of that object here. And so you should think that if I have a vector space, this is a projectivization of it. So I can sort of linearize it if I like, but I can also think of it in an ambient projective category. And so there's this sort of quotiented group of automorphisms. And here's an induced map because these are sub-categories, subgroups of these categories. And the setup that I want to think is that I have a projective representation of some group in this category. And that whenever this happens, there's some extension with B, which has a linear action on that object in the original category. Okay, and so now the upside of this is that oftentimes this is classified, in fact, even just by C, which is a map from DG to B to the D+1 C star. And the upside of this is supposed to be that this defines a homologic class in degree D+1. And so this is how I'm supposed to make contact with more traditional classifications of things like this with group homology. And so I promised you an explicit example, so let me do that. So I'm happy to talk about non-extended theories, and those are valued in vect or maybe hill. And we'll do an example of this projectivity phenomenon for that dimension. Okay, so when t is equal to 1, the targets that I'll take here is I'll get that. That. And the thing that I'll take for T, T2 is out, so that's the Morita 2 category of algebras. And now the idea is that there is something very important I didn't tell you about this, which is that this error factors through the units of that target. So when I write cross here, I mean the maximal subgroup void. And so I throw out non-invertible objects and non-invertible morphisms at all levels. And so the thing that you should think that maybe appears there usually is something like just scalars. It's this sort of suspected C star. And indeed, if I'm over C, that's what happens here, right? So if I take a trivializable algebra over C, this is some Azumaya algebra, it's just a matrix algebra. So there's really just one of these with automorphisms. And so this, right, so we should think that in here we have something like BGLB, and here we have the BGL, and really what I mean is some kind of groupoid quotient where I move the U1 up in degree, but you can think of the classical quotients of group as well. That would just be a sort of representation of the category. And so if I have a projective representation, that's a map like this, and there's always a lift like this. And so now it's the first place where just a bit of analysis will enter. And what I want to eventually say in this 3D setting is that there's a representation theoretic interpretation of what I said. And that really there needs to be a bit of analysis at some point, because even in classical representation theory, there has to be a bit of analysis.
So what exactly is P vect?
Yeah, so I'll say that right now. So P vect, it's yeah. So the general, I can maybe I'll get. So here's a definition of P vect, and the general definition you can probably guess from this definition. So they're all of the arrows in this category that go from the unit to an invertible object. So let me write that up. So I have unit and out, and then I have a module over some Azumaya. So this is an invertible algebra, and so that's some over C. That's some matrix algebra, and then I'm just looking at some module. So this is some finite rank module if I'm in finite dimensional vector spaces. Okay, so that's an object, and another object is say this. And a morphism is an invertible map in the target, so it's important that these fillings have to be invertible, and then first a filling of that diagram. So just to spell that out, it's a linear map from that module to that module. That's maybe twisted by some invertible Morita map between the columns.
So P vect is a space then, because it's only has invertible morphisms. Yes.
So P vect has, so yeah, so this is one description of it as a, I mean, really it's sort of like a bicategory. Another bicategory description of it is I can say that each object is represented by still is the finite dimensional vector space. And now, so I wrote it this time, so read that way. So those are now just my objects. My automorphisms are linear maps. And then now I'm saying that it's the 2 category where, as you say, they're all invertible maps, but I'm saying that I can have a map between linear maps when they differ by a scalar.
But how's the same? Because I thought you said here the objects are morphisms say from C to N.
That's right. Then there's a functor from here to here that sends a vector space to it as a bimodular over C and C. And that's an equivalence of bicategories. And so you can see that whenever I have a map like this, it'll induce one of the bimodules over C. But because of the fact that if I see in both of these places, I'm sort of allowing it to differ by a base here, that will allow these parameters to be incorporated.
I'm still understanding at a fundamental level. You're saying that the objects are what are a module from C to A, right?
That's right.
And then the morphisms are another such thing. A diagram that completes which has an equivalence. So aren't all such morphisms equivalent?
This is an equivalence of algebras in the Munich category. This map is
Oh,
not an equivalent.
That's what I was missing.
Thank
Got
you.
it. Thank you.
So this is just any linear map that might jump. Yeah, so
Got it. Thank you.
yeah.
Map E omega T to T. There's some assumption for you there.
This is for this. Okay, so I didn't tell you the definition of that, but I can. Already sort of morally, it's the arrows in T. I go from the unit to the invertible. So this is a good notation, but you can read the arrow category that really goes into this instruction. So that's this instituting ideas for free, and then also three times over again. And so this map, so T star is just forgetting the arrows, it's just remembering the invertible thing. It's nothing complicated. Okay, so I just wanted to say this sort of general story to indicate that it works in general, and then I'm going to indicate it in dimension 1. And now my claim is that the point is, so in dimension 3, I go fuse to P fuse to her fuse in this dimension. And then this sequence is built. So you can follow the discussion earlier. And so what I mean by that is that what I wrote before about this thing that I was calling WRT, and could maybe be compared with what's usually WRT in low codimension, is not just an honest functor from a cobordism 3 category. Again, strictly what I told you was using the cobordism hypothesis, and I never wrote SO on the board, so it's framed. But you might believe that conjecture, and then you would believe that this is really oriented. And this is a functor into sorry. So the point being here that the point is A. All right, and now that I've set up all this formalism, I can sort of explain the upshot. And so the point is that if I take a non-degenerate diffusion category, and I take the funding 2 group, which is acting on it via functors, that group will act on the WRT theory as the anomalous theory. So I'm going to write that.
So P fuse is now a 3 category. This is now an untwisted theory.
Yeah, so let me go into detail. So T fuse is a 4 category, and the only 4 morphisms are invertible. So what you can think this P thing is doing is taking a target category that you started with and adding an extra C star at the top that's just giving you a little headroom for scalars at the end. So if you're ever checking a coherence in life and you're sort of expecting 1, but you got something else, now you're fine, you're safe. This category lets you just have this extra. Yeah, so let me say in words. So P fuse is the target for twisting. So if it's a trivializable twist, then it can be risky. It can be sort of factored through fuse, but it can't always be lifted to fuse. So, yeah, sorry, maybe I should just write the diagram. So, Okay, so this is some invertible, so this is just some four groupoid. This is really some four category, but the top is just invertible, and the three category part looks like fuge. And so the idea is that you have theories like this WRT theory, which are maps like this. They don't always just lift. Sometimes you need to pass with some word tilde. And so this was already a notion that Siegel had in his original paper on CFTs, these extensions of Bordas categories. And this is a very general story. And so this is one instance of this is when people write that introducing a signature structure or P1 structure allows you to trivialize the anomaly of RT. And so this would be some extended Bordas category. The problem with doing this in general is that by word tilde, this thing might not include the point. And so if I have the WRT theory here, that's defined for a graded category which isn't a Drinfeld center, then there won't be a point in this extended Bordas category. But this is still sort of you can contemplate. The point being that if this is not essentially surjective, this is a fallback, so that won't be. So if the point, so yeah, so if there's nowhere for the point to go, you can't have the point in the extension. That sort of works in that sense. Okay, and so now I want to say the theorem. Okay, so the theorem is that if a finite, the finite two group acts to be a grade of so it has a map from G to this category, this group like category. So those are functors and natural transformations. So there was already a bit of coherence that maybe had to do. The point is that this is for a finite two group. You could take the whole thing if this fusion is finite. That's fine. So if that's true, then it acts projectively on the WRT. And so part of the theorem is that there are multiple ways to say this. And one way to say this is that using a sort of sandwich formalism, if you like these sort of generalized symmetries, and that is that WRT can be thought of as an automorphism of the trivial 4D theory. There's also a 4D theory, which is finite, let me write Zygar-Witten for this finite two group, twisted by some cocycle C in dimension 4. And so there's a regular module for that, there's a forget. And the statement that it acts projectively is that there's an upgrade to a boundary theory of this twisted diagram, which I'll write as WRT. And then when I forget that action, I get the T back. The other way to say it is that I have a Bordas category with background fields given by maps that finite two group. I can restrict within that Bordas category to the underlying frame Bordisms. And now the claim is that there's the original map to P theory. And then you can always lift this to some WRT tilde. So I wrote them both as WRT tilde. They're sort of different objects. The claim is that they're equivalent and they're canonically defined by the data, such a functor from G separated other equivalences of A. Okay. And so now there's some corollaries of this. And I don't want to say in so much detail because I'm running a long time. Yes, please.
So you mentioned two group diagram-splitting theory twisted. What you twisted by?
Yeah, so I twisted still by so the two group I can look at its classifying space and I can look at a map from that to a KC star 4. So that's the thing I was twisted by. So concretely, so I can sort of describe it in pieces. So let's say I have the two group as a cross number. So I have these two groups. So or maybe I just have the Homotopy groups, which can be cross number. So the bottom Homotopy group, it just looks like a group cocycle on that. And then there's a piece of the forecast cycle that's sort of defined on the second homotopy group. And that piece looks like a quadratic form because it's a degree 4 class on a KH, and so that's the quadratic form on your plane with that. And then there's some compatibility between those and the k-invariant defining the two group, which maybe is sort of hard to spell out on the board.
Sorry,
Yeah.
can you say again, this is board BG?
Yeah, that's Fordisms with a map to BG, so principal G bundle, and this is just some finite group, so you can sort of think of this maybe like a cover or something. In terms of the Fordism hypothesis, rank theories are classified by a functor from a point to the target, localizable point to the target. These are classified by a functor from BG. So they're sort of an object with a G on it. Okay, and so I'll just say inverts, maybe one corollary of this is that, so if A is vector space is graded by a metric group, so if it's some finite abelian group with a quadratic form, then this theorem gets you that there's some functorial, projectively functorial quantization of metric groups, because you can write down the associated WRT theories and the orthogonal group of A. So the upshot of this is that the orthogonal group of A with respect to Q is the truncation of group A, and so this tells you that you sort of have a coherent action of that finite orthogonal group on these WRT theories. Yeah, so I was going to give a sense of how the proof goes, but to just give a very general thing, this is sort of the homotopy theory in DNO. That sort of is the engine behind this theorem. And so now sort of what I wanted to say at the end was just that one really wants to sort of just run this machinery where I start with A as this graded C star category of super selection sectors. Right? But this sort of target is not suitable for that kind of thing. And what I really want to do is pass to something that's much, much larger. And so I want to suggest that there's some world that, so there's various versions of this. I want to mention this sort of 5 categories that do a very good job at including those kind of objects that look more like that, and in general sort of C-star graded monoidal category literature is quite developed, and so there are a lot of names to write. And so I mean Peter told us a lot about the Leslie and of course being original sort of that's their pro. And then for these 5 things, short break this and Chinese and okay, so what I want to say is that this sort of world lives inside of some larger world that fits into a story that I've been thinking about in terms of continuous staging. And so to sort of catchphrase for this is that I want to use objects from this for these instructions that appear in this. And so I think this word is being used very differently instead of font or something, but explicitly what I want to say is that given some super selection sector category, I want to really write down something which now word 3 I really need to put close, because I didn't say anything about the kind of extra structure that's on that, or the compatibility, or the dagger structures. I didn't write all the names of the dagger gang, but I think it's that there's something which is a projectization of some kind of algebra object and some kind of liquid categories, which are a sort of version of complete objects. It's sort of something like topological vector spaces. So the point is that when I move to codimension 1, this is some big category that at least contains Banach objects. So it at least will contain things that have unitary representations. So when I write stories like this, I can really write back some GT to the unitary group and the projective unitary group, and I can incorporate things like the metaplectic representation, the data representation, and things that are really are necessarily of more analytic nature than what I wrote. And so really, we might say this is overkill, and that's true, but I want to incorporate a sort of derived algebraic geometry formalism here, because I want to talk about continuous gauging. And so I want to do things like vector spaces graded by a finite abelian group, or maybe two vector spaces graded by a finite abelian group living in dimension 4, working relative to that and gauging it. So for that, I need to talk about categories of sheaves on locally compact Lie groups, things like this. And those do have dualizability properties in these more complicated categories. So you can look at things like OG modules in this more smooth world, and those have, so in algebra 2 of this thing, we believe it to have 3 dualizability, and algebra 1 of PRL, it seems to have 2 dualizability for a locally compact group. And so you can make a lot of that sort of story formal, but you really need to be in this sort of or C infinity version of derived algebraic geometry. And to get compatibility with these kind of arena categories, you really need to pass to this bigger world, because if I look at these sort of smaller categories of Banach spaces, they aren't abelian categories, so I can't take their derived category and use the sort of techniques that I want to from traditional derived algebraic geometry. So yeah, that's kind of the point I wanted to get to. I thought it was a nice sort of bond mathematics, like sort of 3 Peters. We have sort of twisted theories and Schultz-Teichner type things. And Peter told us about these C star graded super selection categories, and then the sort of Whitman categories appear. I want to think about this derived geometry, maybe just as like one concrete thing before I finish. So there's this huge width group, and I think I probably wrote it somewhere. So pi naught of this is huge. It's infinite. It has a bunch of even torsion, sort of mysterious thing having to do with this central charge, anomalousness. But it seems to be the case that because this liquid setting, the analogous objects actually become trivializable, right? And so there are these classification effects that rely on these different non-trivial homotopy groups, and this analytic setting, which is also maybe to be expected when you talk about so just like the bigger representation itself, if you're in kind of dimensional vector spaces, won't have any morphisms to the unit that are fully divisable, but it does have L2 functions. And so that thing doesn't have full divisability, but it is, of course, a relevant number space that needs to be a part of it. So okay, that's all I wanted to say. Thanks again for